accomplished. I actually developed a quantum computer based on Android platform during my PhD and postdoc. And here in the School of Physics, University of Hyderabad, I am trying to develop the same over here in India. So last time I was talking about using quantum machine learning, how we can develop a quantum classifier which can work better compared to cloud.
Excuse me, sir, you are not audible. Dr. Karan?
Hello?
Yes, please. Now you are audible.
So actually I spoke quite a lot. So this is the first time you are hearing, or you didn't hear me at all?
No, when you just started this slide, then just 1 minute approx.
Okay. So yeah, now it is clear, right? Voice is clear.
Yes, perfect, clear.
Okay. Yeah, so today I'm going to talk about, as I was saying, about the advancement of quantum technology in the field of quantum sensing, basically by using the platform of trapped ion system. Now, when we talk about sensing, like advancement in sensing, that is basically talking about improving the precision. Mainly, if we want to measure some physical quantities, which is of our interest, like time, frequency, electric field, magnetic field. So that needs to be measured with high precision beyond the limits of classical technologies. So that is what I'm going to, one of my experiment that I did 2 years back. So I'm going to explain that thing. But before that, let's discuss what do we mean by precision and accuracy. So here is a pictorial depiction. So in the left one, you can see, I don't know whether you can see my arrow or not. So yeah, so the left one where I have written precise but not accurate. So you can see this is not accurate but precise. So this is my experimental data which I have been. I was let's assume that I was doing some experiment. I was measuring some frequency, some oscillation frequency of an oscillator, and then I got this value. So this is precise but not accurate. So accurate value I was expecting is supposed to come inside this, close to this. Now, if I move to the second one, you can see these are accurate but not precise. So this is within the first circle, but it is not precise. It is like moving around. The third one, if you look at, it is accurate and precise. So that is what like we mean is accurate and precisely meaning like if I measure the frequency for n number of times, the value will become like will be a like the sigma deviation or something like that. Like it is not like the first, like the left one picture. It will not be like that. It will not be like the middle one also. So that is what I mean, like precise and accurate. So here we are going to talk about improving the precision. It is accurate, but the precision is not that much. So we need to improve the precision. That is what I'm going to focus. Now let's take an example, which is basically an example of a watch, maybe wristwatch. So like the first one, if I in the left corner you can see the watch over here, that is the wristwatch and is based on analog oscillator. Analog oscillator meaning pendulum I'm talking about. Initial days like 17th century when we had clock, we had it was based on pendulum actually. So when you compare your watch with others, you are checking whether it shows the correct time. That is accuracy. Like here you can see in the corner one, it is showing 10 point like how it is like 10 o'clock, and then this is around close to 15 minutes, right? But it's not 15, it is between 10 and 15 minutes. But we do not care whether it is 15 or 10. It doesn't matter to us. But it matters when you are doing some work, like you have to appear some interview, or you have to catch some bus. So buses run on time, right? So then you need to synchronize, or you need to adjust your clock with the bus time, right? So that is what you can do because you are using analog clock. So that is where it comes, like why it is very important, whether it is 10 past 15 or 10 past 10, that is how it matters. But in everydays, it doesn't matter to us. But when, let's say, you are sailing in an ocean, now you don't know anything. So how do you know where are you? So that is the problem. Nowadays, it is easier because of having global positioning system, GPS, what we know. Before it was not there. It was based on like fixed position of some star, something like that. So now what I say, so let's say you have this kind of analog wristwatch. Now and it shows correct time. But if we observe carefully, not all clocks show exactly the same time. There is always a small variation, or what we call like tolerance between them. So that variation reflects precision. So if your watch is off by half an hour or 1 hour, like in everyday, like the clock or the wristwatch, what we used to wear, so then clearly the accuracy is poor and it needs correction. That is not the precision, that is accuracy. But even smaller deviation matters. Let's say it is 10 minutes or 15 minutes, then we do not take care whether it is 10 minutes or 15 minutes. But if it is more than half an hour or 1 hour, then it matters 2 hours in everyday life. So it is accurate, but to what extent? Like if I am saying some time, let's say it is 10, then 10 plus minus how much value is there. So that matters. Like it depends on the work what we are doing. Mostly if we are somewhere, there is no other reference clock that you can synchronize your clock, then it matters. So like the bottom one is the current like modern wristwatch. It is basically like based on the GPS, so it doesn't matter. But previously all the clocks were based on pendulums, and the pendulums was made like it is man-made, right? Like so there will be a manufacturer like who is good enough, how he is preparing, how he is manufacturing all these things. It depends on that. So let's go to the next slide. So, so now I'm going to, since I'm going to talk about the sensing application. So what is in the right corner, you can see here, I'm just showing just two levels, right? So, I mean, you can use it as a clock. Actually, nowadays, the precision based on atomic clock. We are not using any more pendulum based clock. But atom meaning we usually like assume as a two-level system, then we drive a transitions, and then we measure the frequency, and that gives us the time reference. So now here, like our goal is to measure how precisely you can measure the frequency. Now another example, you can see the animation over here, how precisely we can measure the oscillation frequency over here. So like with minimum uncertainty. And the other example is that we all know about spin of an electron. The magnetic field is there. And this because of the magnetic field is there, so electron start precess around the magnetic field. But what is going to happen if this magnetic field is oscillating magnetic field? Then it will not be that easy to estimate the frequency with high precision, like minimum uncertainty. What will be the minimum uncertainty? So till now, what we know, what will be the uncertainty? So that is basically depends on Heisenberg uncertainty principle. The right, what I have written over here, which is the frequency, and that is proportional to 1 over t. T is the observation time. or the experimental time. So now you can see, so that is the precision which is determined by the Heisenberg uncertainty principle. So that is the limit. You cannot go beyond that. So now let's go to bit evolution of atomic clock or clock. So the left plot, what it is showing over here, it is like over the years how precision have been improved, how they have reduced the uncertainty. And now we are in a era of atomic clock, and where the uncertainty is 10 to the power minus 18. So now the thing is that what is the purpose of improving this precision? Like it started from like before 1950s, right? So what is the purpose of improving this precision? That will come to, like we will explain, but now also here I'm actually showing, so this picture I have taken from the Wikipedia. So this is the evolution of clock, how like our clock, the shape is changing, and so and also the structure is changing. Now we are in the era of mobile phones, which is like the time is based on the GPS system. So initially, there is a problem with the pendulum clock. It is basically frequency what we are determining, that is based on mechanical oscillation. Then we move to quartz clock, that is basically the vibration of the crystal. And now we are in the era of atomic or ion clock, which is basically the atomic, based on atomic transition frequency. Now, why it is more stable in case of atomic clock? Because it is natural. The levels, the energy levels are natural compared to the other clocks. We'll also discuss about that thing. What is the difference with the other clocks? So, so now, yeah, this is what I was telling. Like when people found the problem, like when they are sailing in the ocean, how they are going to determine their position. That was very difficult at that time, because if you see the latitude, they can uh, easily determine, but the longitude, it was not easy for them. Why? Because in case of latitude, you can see from the this right picture over here. So they usually follow one fixed star which is not moving, like the North Star. So then, based on the position of the star, they can get the angle, and they get their position. Like that is the, like if the angle, the measured angle is around some 30 degrees or 50 degrees, they can say okay 50-degree with respect to the North Star. That is with respect to the latitude. But what about longitude? Because if you see the longitude in this figure over here, because Earth is rotating, right? So if it is rotating, how they're going to determine their position very well? Because there will be a time dilation. That time it was not there, time dilation, because of Einstein, it came later. But they found that there was a problem, and they experienced this kind of problem actually. So for the latitude, so what they usually does, so this North Star, this is fixed. With respect to that, they have some angle measurement instrument. By that way, they can tell the, with respect to the horizon, that is the angle. But with respect to the longitude, it was not possible, because Earth is rotating around this axis, right? So the time is varying. So that is why it was difficult. And like that time, sailor also like found that problem, uh, because Earth rotates 360 degree in 24 hours, right? Meaning 15 degree per hour. So 1 degree every 4 minutes. So the time is changing in 4 minutes. I mean, in every 4 minutes, 1 degree is changing. So that is very difficult. So, and if we calculate, so then what happened? Actually, the story was there something like that. They were sailing. So that is in 17th century. So they know the latitude very well, but the longitude, they, because it is varying, so they were unable to calculate, and the calculation was like 1 kilometer off. And there was a kind of, sad news was there. That is from the British sailor. You can go and check. I mean, that is really, yeah. I mean, so that is how. And then after that, the British Kingdom, they declared huge amount of money who can invent the clock with high precision. They can give huge amount of money or something like that. That story is there. So that was the problem. Now, yeah, here I was showing, like in the left side, you can see like the errors. So that is actually this already explained by Dave Wineland, the Nobel laureate, while he was explaining the atomic clock. And he showed that, because of this like 1 second mismatch, the difference.
Excuse me, Dr. Tarun, you are disconnected, I think. Your screen is visible, but your audio and video is not here. Dr. Tarun, can you hear me? Can you please confirm me?
Yes,
Yeah.
I can hear you. I can hear you.
Okay, sure.
I can hear you very well.
Now your audio video is clear.
Okay. Uh, Now it is clear, right? It is audible.
Yes, audible. Video and audio, both good.
Okay. So, yeah, so this is the small calculation I was showing. Like if there is a 1 second mismatch, then what will be the difference? How far they are from the coast or something like that, they can calculate easily. So that is why they are like, that is the purpose of improving the precision in clock. Now in the era of atomic clock or iron clock, and we have GPS, global positioning system. So we get usually signal from satellite, and then we can synchronize our like clock. That is very easy nowadays. And when we are using this kind of crystal oscillator, like the clock based on Ford oscillator, that time 1 second discrepancy in the time gives us around like half of a kilometer um, in position. That discrepancy was there, but now since the resolution or since the precision has been increased in case of atomic clock or iron clock, it is around so that half of a kilometer now reduced to 30 centimeter. So that calculation I was showing it over here in the right side of the slide. So that is how it is improved because of improving the precision actually. Okay, then so now I'm going to talk about atomic clock. So in the left side you can see like these are the main discrepancies. Like time period is proportional to root over L over G. L is the length of the pendulum. So that length is a metal, and it varies like with temperature, friction, and then mechanical drift, and also the manufacturer defects. Everything will be there. That is why every clock are different. Their time scales are different. But in case of atom clock, they mostly depends on fundamental constants. And the other things is that if the clock based on atoms or ions, they all are identical. There won't be any kind of manufactural or like mechanical problems because it's natural. Like all the atoms are generated or produced naturally. So like there is no two different atoms or different ions. So this and now in case of atoms, what is happening? Basically, we initial the how the oscillation happening. Basically, we initialize the atoms over here, then we apply the radiation, and this radiation, this can be any kind of like microwave or any other RF. That's also possible. So that depends on the energy difference between these two levels. And if we apply, then the population will go from here to here, or atom will move from this one state to this two state, the state which is designated as 2. So now once you move it over there, it can, if you remove the drive, then it can come to 1 because one state is the ground state. So it will decay to ground state. But if you drive, if you continuously drive your transitions, then you can measure the frequency, and that formula you already know, it is derived by Planck. So that is how we usually get the uh, definition of frequency, and from there we can estimate the time. So that is the time uh, reference for atomic clocks. Now, how we usually realize, basically that is a superposition of between 1 and 2 states. So this animation again is not working in this. Yeah, so that is what I was trying to show, like how like atom is oscillating between 2 and 1, and each oscillation is giving you 1 second. Okay. So now, why atomic clocks? What were the discrepancies? I have already discussed, but here I'm just pointing it out. Main problem was like manufacturing tolerance. So that is not there at all in atomic clocks because all atoms are identical. And the thing is that atoms don't wear out. Like which time atoms doesn't degrade. But in case of clock based on pendulum, because it is a metal or some material, right, over the time or over the years, it will degrade. So then the time will be also the, like the precision, accuracy maybe will be there, but the precision will not be there. So in that sense, atom clocks are better, and the precision wise, you can control, you can improve the precision. And here I'm going to talk about how that precision can be improved in case of clocks based on iron. And my platform is iron traps. And this iron trap, like there are three guys who have invented this how to trap an iron. One of them is Woodland Paul, who is actually invented linear Paul trap. And the other guy is Michael Penning, is Penning trap. So here, advantage. So in case of atomic clock or iron clock, there are few advantages. Like you can trap a single ion, and then you can cool them. You are cooling meaning you are reducing their motion, so that the probe laser, like, or probe field what you are applying for driving the clock transitions, so the line width of that transitions you can reduce. So that is one advantage in case of iron clock. So these are the advantage what I have pointed it out, because in this case, uh, iron is inside the vacuum chamber, so it is isolated from the environment. So it is not like talking to the environment. So the degradation is not there, and you can reduce the energy, kinetic energy of the trapped ion, so that you are in the lambda decay regime. So by that way, you are reducing the kinetic energy. Meaning you are reducing the external motion, like motion of a trapped ion system. Now you can have multiple atom, you can have single atom also. But here I'm going to talk about single ion, and how to trap a single ion, that I'm going to describe over in a couple of slides. So now, if you have a highly accurate and highly precise atomic clock, then you can do many like fundamental work, which is based on one of the work is like dark matter search, like those because we know dark matter exists. That experiment has been done, and we have seen the existence of dark matter, but still not discovered yet. So if we can develop this highly accurate and precise atomic clock, that will also help us to realize the presence of dark matter. And then the other one is like gravitational wave detection, that has been done recently also. So the context is, we are not going to improve the accuracy. we are going to improve the precision. That is our intention. And the precision that is already been limited by the Heisenberg uncertainty principle. Because let's say we want to measure the frequency, then it is limited by 1 over t. T is the observation time. That is there in the theory. But one thing we have to think about, this is only for time independent Hamiltonian. So that is the important thing over here. Now the context is over here, like if we can improve like this precision, then it will be very useful in order to implement many fundamental work. But here I'm showing some example. So like one is like that estimating noise in clock frequency, because clock frequency based on ion is basically two level, right? Two like energy level. Now if there is, and it's electric field, I'm driving it, driving the transition, meaning I'm applying an electric field. Now how good it is, how like the field what I'm applying, how good it is, meaning whether there is a effect of noise, how do we know? So that is the thing we, if it is not known, we will be able to know it. We will be able to know it. So that technique I'm going to discuss. So this is our context. Like we can uh, like estimate the noise in the clock frequency, which is reducing the precision. We can also estimate some unknown noise frequency, which is disturbing our systems. Like, and also in case of dark matter meaning there are different kind of dark matters, like weakly interactive massive particle, like axion like massive particle. So those things whose mass range is in kilohertz, that is also possible to detect them by, like if you improve the precision, then that is also possible. And then gravitational wave detection, that is also another thing. If you remember, like this signal to noise ratio is very poor. So you are increasing the precision, meaning you are increasing the signal to noise ratio, so that you can detect your signal very well. And also in quantum imaging, quantum biology, quantum imaging, meaning there is, you know, MRI, like in when we go to the hospital for MRI or NMR. So the problem is um, like if there is, so I think you know how that works. They usually send some signals, and then they check whether there any tissue is damaged or what happened to the tissue or something like that. So the thing is that the frequency what they used to give, whether there is any noise. So sometimes it is very difficult to understand, is there any damage or not in the tissue itself. Like when they see the MRI image, they are unable to understand because of the noise. So, and because of the frequency what they're applying, that precision is not that well precise. So that is another thing. Like if we can improve the precision, then there like many things can be improved, starting from estimating noise in clock frequency to quantum imaging to quantum biology. So now I'm going to just briefly talk about ion trap quantum computer, because this sensing has been implemented on ion trap. So how to trap an ion? Ion is a charged particle, right? So like as we know, if we want to confine a charged particle in space, we need electric field. So, and how are we going to apply this electric field? We need some metal plate, then we can apply electric field, right? So that is very basic. Now the problem is we want to confine it in space. How are you going to do that thing? So here I have shown you some pictures over here. You can see the arrows are there in all three directions, right? And in all three directions we are applying field. Now, is it possible at all if we apply GC field or static field in all three directions, whether it is possible to confine? Answer is no, because it will not solve, it will violate our Laplace equations, which is delta phi, del phi equals to 0, phi is the potential. So, in order to confine in space, you have to have an AC field. So that is why in the animation you can see these arrows are moving, changing their direction. If you see it carefully, the arrows are changing the direction. That means in 2D, in X and Y direction, we are applying AC field, automatic field, and along the Z direction, we are applying DC field. Okay. So this is a combination of both RF and DC field. By that way, you can confine the ion in a potential value. Now you can see in the bottom animation, ion is trying to escape because of applying the AC field. The arrows are changing the direction, right? So sometimes it will be minimum, sometimes it will be maximum. But you see the time it tries to go away from this minima, the potential is changing. So here, one thing we need to consider that the motion of ion has to be very small compared to the oscillation frequency of this driving potential of the RF potential, what we are applying. That has to be taken care of. Otherwise, it is not possible to create a saddle potential for the ion. So that is the basics how to traffic that particle. Like you cannot have a static potential in all three directions to confine space. So that is like the first pillar of if you want to develop a quantum computer is trapping and cooling an ion, and that is why you need to cool the ion also simultaneously while you are trapping. The second one is the like let's say you trap it, then you are doing some kind of experiment, and then you need to read out, otherwise you will not know the result. And that depends on that comes to this right side qubit readout. So here this is the energy level diagram. So here I am going to talk about barium ion because yeah, I work with barium ion. And here you can see, I have shown here in this energy level diagram, S half to P half, I'm driving one laser, and this is like blue color laser. And if I drive it, it goes to P half, and then it is coming back again S half. So if the ion is here, if I prepare the ion over here in this zero state, then I can see, and if I drive this transition, then I can see its presence. But if it is not here, if the ion is, let's say, in the hybrid state, then even if we drive these blue uh, transitions, blue drive, we will not see the presence of ion because ion is self to the hybrid state. So that is what, like qubit readout, you can see like the corner on the right side, you can see like when the ion is at zero state, if we drive this transition, then we will see the signal. So that is over here, the photon number, you see from 5 to 20, this right? This is Poisson distribution. And the left one, when it is not here in the zero state, it is in the defibrillated state. So meaning that is self, that is not in the zero state, that is in one state. But our qubit is in between zero state and one state. Qubit is basically meaning two level. It's an atom which is equivalent to a two level system. So this is the readout. Like if you prepare your system and then if you want to do some experiment, do it, then you measure the system. How are you going to measure the system? You have to measure the population, whether it is there in the zero state or in somewhere. So in order to measure the system, you have to drive the transitions. Here S and P are the dipole transitions, and you have the corresponding layer. You are applying it, and you are getting over here the probability. Now the third one is the logic gates. Like since it is a quantum computer, right? So this is also one important thing is that how good you can prepare your qubit. The qubit is basically here between 0 and 1 state. Why it is between 0 and 1 state? Why not between S and P state like other state? Because S half and D 5 by 2 is a quadruple transition. D is metastable state, and P and S is a double transition. Okay, so the lifetime of D is quite high compared to P state. So there are also the advantage. That is why we are choosing this 0 and 1 between S half and D 5 by 2 state. By the way, this is atomic energy level. Okay, that is what that is what I'm saying. S half P half. This is atomic energy level. So now the qubit is in between 0 and 1, and this is different layer. And you are driving. If you drive this one, then you will see the oscillation over here in this picture, which is known as Rabi oscillation. So Rabi oscillation will tell you the information of quantum gates. What kind of gate you want to prepare? Like in digital quantum gate, you know, like if you want to apply NOT gate, then you can convert 0 to 1, right? Or if your input is 1, it will convert to 0. But similarly, in quantum gates, if you apply pi pulse or pi gate, then it will actually behave as a digital NOT gate. Okay, so here everything we realize in terms of rotational matrix, and that is, I mean, here you can see this rotational matrix is r theta phi, what I have written it over here, and the animation also, I guess it is not working. So yeah, you can see now here the animation. So this is like if you want to apply along the y-axis, around the y-axis, that is ry gate. So that is the animation you can see over there. So these three things are like if you want to realize quantum computer, these three things are three pillars, are basic pillars to develop quantum computer. Now let's go to the next slide, which actually I'm showing the real trap setup. So the left corner one, that is the electrodes, and this is a linear power trap. You can see the electrodes over here, and so there are these electrodes where I'm applying the AC voltage, and which is confined, which keeps me confined along the XY direction, and the other one is along the Z direction, which keeps me confined along the um, Z direction. So this, like both DC and AC, they are applied. And when it is mounted on the flux, because we have to go inside the vacuum plug, like vacuum chamber. So first we have to mount it on the vacuum plug over here. And this is a schematic you can see in the middle figure. And the iron trap is there. And also there are some optics, like you can see the lens. Lens is also there, close to like the trap, like on the blade, because and this lens also will go inside the vacuum chamber, because if you want to connect fluorescence, like more fluorescence or photon, then you have to put it inside the vacuum chamber. So now if you see the right one, right corner one, so that is the overall setup. The vacuum chamber is there, and inside, like the trap, how we have mounted, it is shown over here, and it is inside the vacuum chamber. And then there are other accessories which we need to run this computer. Now, once you prepare it, then you can see the just right side, the middle figure. So this is now all the optics are aligned, because lasers needs to go inside to the vacuum chamber so that you can talk with ion. Like if you want to do experiment, you have to pulsing all the lasers which is communicating with the ion. And so this is from the outside. So the alignment, how you are aligning all the lasers going inside the vacuum chamber. And you can see the coil over here, right? This coil and the big coil over here. Those coils are known as Helmholtz coils. Hope you know. Helmholtz coils are used for generating magnetic field. The current is flowing through the coil, and that will generate magnetic field. And the trapping region, which is very important, trapping region. The whole trap, I am showing it over here, but the important region or trap volume is this one. The middle, you can see like I'm zoomed over. So these like a needle-like electrode, those are where we are applying DC, and these electrodes, blade kind of electrodes, where we are applying AC. Now, this open region, you can see it over here. Here, the ions or atoms will be trapped. Ions will be trapped. Okay, so this is the trap volume or trapping region. And in this region, we want to have the uniform magnetic field. That is why we have a like pair of Helmholtz coils, which will help us to get uniform magnetic field. And the trap volume is something like this, is determined by this, because trap volume will tell you how many qubits or how many ions you can trap in the system, or your quantum computer can have. Now, once you prepare your system, then you can have your ion cloud, you can have linear chain, you can have rotor. So you can play with it, because you are applying both DC and RF field, and by playing DC and RF, you can prepare this kind of configuration of ion, depending on the kind of experiment you want to perform. Okay. Now, as I was saying, I was using barium. And this is the energy level diagram. All the lines, arrows are you are seeing, that is the addressing energy level. And it is mostly all the lasers are in the visibility. That was another advantage of using barium ion. And the qubit laser, what we are using, it is between S half and d5/2, as I was mentioning, and it is denoted by this blue color line, which is 76 to 9. Now, what is the meaning of qubit over here? Qubit, like, if we have this many number of ions over here, take a single ion, and single ion can be treated as a two-level system. And now, so this is a qubit. If you want to realize, you can go to the block sphere, the right side. And the block sphere, two poles are two states, like zero state, which is defined S half, minus half, d5/2, and minus half. So either you can prepare in zero state or in one state. Okay. But because this is quantum mechanics, so you know the advantage of quantum mechanics that you can prepare superposition of state, which is not there in classical computer. Classical computer, you have only two states, either one state, either you can have one state or zero state. But here you can have intermediate state, which is called superposition state, including both zero and one state. And ion can simultaneously stay in all the states. That is the beauty of quantum mechanics. And that is the advantage of moving from classical computer to quantum computer. That is why the memory wise, it has also a huge amount of memory that it can store. Now, so here I was just showing any kind of experiment if you want to perform. These are the steps you have to follow. In the left side bottom corner, you can see. First, you have to do optical pumping. Optical pumping meaning you are preparing or you are initializing your system. If you do not initialize, then you don't know where is your system. To do some experiment, you need to first prepare your system. Then you know the initial state and the output state you also know, then you can compare what is happening or not. So that you can do by optical pumping, the initialization. Then RF and probe, meaning you are driving your qubit laser, you are doing some experiment, like if you want to apply some pi gate or pi/2 pass or Hadamard gate, some other gates. That is what you are going to do. And then you have to do the measurement. Now, before measurement, you can use the solving, like you can use the solving technique, like which state you want to measure. Depending on that, if you want to solve, you can solve. And this is the way of solving. This is what I explained to you before. Like if you are defined to state, so that you can do by solving. Then if you measure, you will not see anything. But if you see something, that means the whole population is not being processed to be defined to state. Okay. So this is the procedure, like mode of operation for realizing this thing. Now, if you have, so in the right corner, if you see, this is the CCD image. So here, before I was showing, we are counting the photon. So that is why you have a signal and you have also noise. But if you see in the CCD, in case of two ions, which I am showing in the right side corner of one, you can see the image. Like when, if we say I trap two ions, both ions are in S state. So you can see the image of them. Now one is being filled to d5/2 state. So that is why you can see the second one, only one ion is there. So the other ion is celled. That also is possible. Like you can individual ion, you can move to some other states and you can play with only one ion. In third one, you can see also the you sell the ion what was there in A state, and only D states that is fluorescing, and that is fluorescing, so that is you are seeing the count. And the other condition is no ion is above observable. So if you see the combination, this is actually generating Bell state, like SF, SD, like 00, 01, 1011. So this kind of logic gates you can prepare. Now, this is on the C schedule. Now, how are you going to check it? Because if you want to count the photon, then you have to use photo multiplier cube, which usually uh, counts photon. You have to give some threshold. Here in the middle figure, you can see where I'm making counting photon. You can see the signal is this one, the right side, from 20 to 60, and from 0 to 20, that is the background count, that is the noise. Okay. Now here it is, you have the important thing is that you have to identify the threshold. Otherwise, you are going to miss some counts, some real photon count. So that is one of the discrepancy. So in atomic or in ionic flux, because the state particle prepare, if you do not measure with 100% fidelity, then there are some errors, right? So that will reduce the precision also. So that has to be done very well. Now, if you the right side bottom corner, you can see how does it look this when we are counting the photon. If you have three ions, so you will see this kind of like Poissonian distribution for three different ions. Now, you may be wondering, like at some point of time, I was talking about S up state and D phi by 2 state. Sometimes I'm saying S up minus half, D phi by 2 minus half, right? So here is the reason. So we are applying magnetic field, right? So magnetic field, so here in the right corner, you can see this is a pair of remote coil, which is giving us a magnetic field, and we need a uniform magnetic field. And if you have a magnetic field, if you see this energy level diagram over here in the left side, so without magnetic field, you will have only one line corresponding to S half, corresponding to E half, EC half, D phi by 2, D phi by 2. You will have only one line. But when magnetic field is there, all the lines will be splitted out that we know because of Zeeman splitting will be there, and that is the interaction energy. And you can calculate all this GJ mean language factor, and then you can calculate also uh, what is the interaction energy, and then you see in the presence of magnetic fields, all the lines will be splitted up, right? So that means individually you can have all the transitions because you can address all the levels. Before d phi by 2 was only one line, right? So the magnetic field. Now you have the six lines. The phi by 2 is J, total angular momentum. So 2J plus 1 is the number of splitting lines will be 6. So you see now 6 lines. So you can now, so from also from S of level, there will be two lines. So from each line to each line, there will be one transition, right? So you can address all the lines now, but it depends on the line of the addressing laser. So that is very important. Now, how are you going to reduce the laser line width? That is important. And how far you can reduce? There is a limitation, right? Optimized limit is there. You cannot go beyond that. So when you are talking about qubit or atomic clock, meaning two level, which two level we are talking about? It is not S half or dependent. It is S half which magnetic level, like which MJ level, that matters. So yeah, so if we drive the all transitions, we're supposed to see something like this. Over here, you see all the transitions, like from plus up to plus minus 3 by 2, minus up to minus 5 by 2. Like we will see all the transitions if we shine the layers between S up and D sub. But we will concentrate particularly on only on one line, which will give us better stability, right? So now, how do we know that which one is going to give better stability? And because if you have all the lines, and if you chose only one line for qubit or your, in order to realize qubit or clock, then how do we know that line, like the line it will be well enough, you can get, you can be, or you can be close to the precision of Heisenberg on 100 degrees. So that matters. But there is a unique way of removing all the lines except one line, which we want to have. How? By this, you can see In the left side, I have shown the schematic. So this octagon is the chamber, vacuum chamber. Inside the trap is there. Now coil, the Helmholtz pair of Helmholtz coil is along this direction, and the qubit laser here 1762 is our qubit laser, which is addressing S half and D 5/2 as I mentioned before. Now, the polarization, the wave vector of this qubit laser and the magnetic field and the trap axis, all these things matter, how they are, and they are going to affect which lines, or they are going to, the filtering choice of all these will lead us to choose particular qubit or particular which two level we want to consider. So now, what is this here in the right side plot? This is, you can see the phi and gamma, right? Phi is the angle between the magnetic field and K is the wave vector, okay? And gamma is the angle between the magnetic field and the polarization of the qubit laser. So now from these three plots, you can easily identify which transitions you want to choose, whether delta equals to 0 or delta equals to 1 or delta equals to 2. Now, depending on the experiment. Now, for atomic clock, or also for sensing purpose, we should always choose delta equals to 0 because it is less sensitive to the magnetic. So that is why we will choose this line belongs to this delta equals to 0. So that is most important. You see now delta equals to 0 will be S half minus half to D 5/2 plus half, right? Then that will be delta equals to 0. So then you will see only one line. And how are you going to choose? You have to, so you have to choose phi and gamma properly so that you can have only delta and 0. Okay. So this is the way like you can properly tune your system, which line you want to concentrate, which two level you are going to consider as a qubit or you are going to use for atomic clock. That is very important because delta M 0 is good because it is least sensitive to the magnetic field. How does it matter whether it is sensitive or not? It matters because because magnetic field, the wave we are generating through this coil, right? A pair of Helmholtz. Now, what is going to happen if there is a fluctuation? Fluctuation of what? Because we are flowing the current is being, like current is flowing through the coil. That is why magnetic field is being generated. Now, the source, what we have, if that has a fluctuation, uh, then that will lead to also the fluctuation in the magnetic field. Now, if there is a fluctuation in the magnetic field, the line what I have drawn it over here, so there will be a fluctuation in that line, right? So then the frequencies, if what you are seeing here, like let's say for plus half to minus half, this line, this frequency, the line will also be increased, or the frequency, the center frequency will be shifting around if there is a fluctuation in the magnetic field. So then that will lead to reduce your sensitivity, reduce your precision, right? So that is why all these things need to be taken care of. So this is one thing. Now the second thing, before going to the second round, let me just talk about or share about the mathematics here for the ion trap systems. So since there are three things, right? One is ion, and how we are talking to ion, that is the laser, right? Laser, we are driving laser to talk to the ion. So there will be three things: the Hamiltonian for the ion, Hamiltonian for the laser, and the interaction Hamiltonian. So that is how it is written. There are three terms, and the interaction part is over here. So this is basically the Hamiltonian for Rabi model or James Cousins model. So the similar kind of Hamiltonian over here. And if you solve this Hamiltonian, then you will get to know the, like, if you drive the transition between S half to D 5/2, which is your qubit, what will be the population? If you measure the population at a definite time, what will be that population? You will get that idea from this Hamiltonian. And this is the expression. You can get it from this Hamiltonian if you solve it using short derivation. And this probability of determining the population in the excited state. Excited state meaning here in this 5/2 state, and it is related with Rabi oscillation. This is Rabi oscillation, gamma, omega, big omega. This is Rabi oscillation, and delta is known as detuning. Detuning meaning, so you are driving these transitions, right? S up to D5/2 with a laser. So this laser uh, is on resonance or with some detuning. So that matters. Now, so this is the Rabi oscillation what I was talking about. And here we are measuring the distant population, and it is varying over time because this qubit laser you are driving continuously, right? So that is why the population is being transferred. So initially you prepare over here, and then it is since the drive is on, so if the population is being transferred here and then coming back here, that is reflecting in this Rabi oscillation. So Rabi oscillation is very important for a system because this will tell us what will be the pi time. Like if you want to construct quantum gates, that based on this kind of this Rabi oscillation. Now, you see, if you apply pi pulse, if you prepare your system either in S state or D state, and then you apply pi pulse, pi meaning so this from 0 to here, this is one complete pulse, right? If you drive your laser and you keep it on for this time, then you will transfer the population to other state and it will come back. But pi meaning half of it, meaning you are completely transferring all the population from 0 to 1 state. But if you apply pi/2, like here, then it can generate superposition. Right, superposition states. Like 50% population will be in S state, so 50% population will be in D state. Now here you can see it over here. So free when yeah, so this picture over here you can see free atom energy levels, right? When it is not trapped at all, but when it is trapped, it will have many energy levels, right? So these are the motional state of ions when you trap it. So ion also like it is a simple harmonic oscillator. You are confining a simple harmonic oscillator, right? So it will have different vibrational levels. So these are the vibrational levels, which is basically the motional state of ion that will be there. So if you want to do some kind of sensing experiment or you want to make a quantum clock, then sorry, ion clock based on quantum based on trapped platform, then you need to reduce the motion of ion. So otherwise there will be problem because of the line width drawdown. You can see it over here. So here I showed you like this is a fringe width which is below 100 like 100 hertz, and if like it is related like this. So the precision also depends on the line width, the probe layer, like what you are applying for driving this transmission. Yeah. So now one important thing is that so the Raman oscillation, what like we are applying the driving frequency on resonance. There is no detuning. That is why we are talking about transferring all the population, right? But if it is detuned, then you are not going to transfer all the population, right? So that is the problem. Now, how do you know that when it is on resonance? That means detuning is completely zero. So this is the effect, the bottom picture you can see, this is the effect of detuning. If it is not on resonance, you see the contrast, like the population is not reaching to 1, population is going down, and the oscillation frequency also changing. If you increase the detuning, the frequency is also changing, frequency is also increasing. Contrast is definitely going down. You are unable to transfer the whole population from 0 to 1. So that is the important thing. So how do you know that you are on resonance? Meaning what? So here you're driving meaning laser, you are applying laser at certain frequency, and you are scanning the frequency, and you are seeing when the frequency of the driving laser is matching with the laser of with the energy difference between these two layers. So that is how you are defining this your driving laser is on resonance or not. That is very important. Now, there are many things. one thing we have already talked about the magnetic field. If the magnetic field is fluctuating, then these level will be also fluctuating. So that will also introduce some kind of noise in your system and will not give you like proper value of resonance frequency, because you are scanning the driving frequency, and when it is matching, you are checking that the population has been transferred or not, completely transferred or not. But because of this magnetic field fluctuation, the lights are also fluctuating. So you will not get any stable kind of oscillation that you can predict. So that is another thing. And this broadening effect also you all know. But when you are talking about a single hour,
Hello.
audible or not?
Yes, now I can hear you. Your screen is not shared. Your audio video is okay, perfectly.
Now it is okay?
Yes, it is okay now.
Okay. Yeah. So yeah, so we saw that like the effect of deepening is there. Effect of deepening also will reduce your precision. How precisely you can measure the oscillation frequency over here. So that will reduce. So we need to know precisely very well effect of deepening. So she, till now we have not talked about coherence. Okay, we saw the effects of measurement. If we do not identify signal to noise, like the threshold value, which one is dark down and which one is our signal down, the error may come from there. Then we are not going. We are unable to identify 100% efficiency. And the second thing is the detuning. So that will also affect how precisely you can know or you can estimate the frequency. The third thing is that whether you are in coherence or not. So basically, there are three things which come to mind. One is dephasing, which is basically magnetic field fluctuation, and other one is like lifetime of the excited layers. That is massive. But yeah, due to some like environmental interference, that will be reduced. Like in our case, we are using D5 by 2 levels, and for barium D5 by 2, its lifetime is around 30 seconds. But due to the environmental disturbance, it reduces to 2 seconds. So that is also another thing which will also reduce your efficiency, because from uh, because as I was saying, Heisenberg's limitation was like if you want to measure the frequency precisely, which is proportional to 1/2 t is observation time or experimental time, duration of your experiment. Now, whatever experiment you are performing, it has to be below 2, right? Because otherwise, the signal what you're going to, so that will be affected. So that is what we are going to discuss. So here you can see I have tabulated here. These are the effects given set that can destabilize the accuracy as well as precision. There is another effect which is stark shift, which I'm going to talk about later. That also can destabilize accuracy. Magnetic field noise, that will come because we have a pair of coil and we are the current is being flown to the coil, right? So how good your force from where you are getting the current, that matters. and the laser phase noise. That is also very important. The laser, this actually line is actually very small, like that. Uh, and you need to lock the laser very well so that there you can ignore the phase noise. So if there is any noise, that will be reflected and that will be used to the precision. And on top of that, there will be some technical noise because electric fields are there and magnetic fields are there. So you have much more instrument which is controlling those fields. So all the technical noise also will be there. So that will lead to reduce the precision. Now let's discuss about the effects of decoherence of these effects. What we are just talking about. How are you going to? So we know these effects are going to degrade the precision, reduce the precision. But how are you going to identify the precision? So in order to do that, we have a very beautiful experiment that is transfer spectroscopy or Ram's interferometer kind of setup, where we what we should, what we used to do is, so in case of radar oscillation, we have continuous pulse is there. Okay, 5 pulse is there. But here, what we are doing, we are dividing this pulse. Like we are applying as pi by 2 pulse, so that we are preparing superposition step. As pi by 2 pulse will bring us to the equator. If you see the blocks here, it will bring us to the equator. And then we are teaching of the probe. So that is the difference from the Rabi oscillation or Rabi spectroscopy. Rabi spectroscopy, we are not teaching of the drive at all. So that is why drive laser, if there is any phase noise or any other electric field noise, that will also incorporate in order to estimating the frequency, right? But here we are teaching of the probe. So that is why we are reducing the noise. So here you can see after pi by 2 pulse, it is freely evolving. So it is in the equator, it is freely evolving. And after that, we are again applying another pi by 2 pulse, and then we are measuring. Okay, and always we are measuring phase will be reflected in the population. If phase is different between this first pi by 2 pulse and second pi by 2 pulse, if there is a phase difference, that will reflect in the population. In the measurement, the measure is constant, right? So you can measure in the Z value. So you have to project it in the Z value. And you can measure the population. So all the information like will be reflected in the population. Here, what we are doing, like in order to know, because we have developed a system, now we want to know what is the coherence type. Because it is not ideal system, right? So this is the spectroscopy method what we are using over here. And here what we are doing, we are this wait time where the probe is not missing, we are changing the wait time and we are measuring the population. Okay? So that gives us, that tells us like what is the coherence time of our system. Now you can see there are 3 plots. Okay, so the first one, like when we were running okay, higher magnetic field. So the fluctuation of the magnetic field is quite high. So the coherence time is very low. It was below 500 microseconds. The second one, when the magnetic field is low, so the magnetic field, we reduce the magnetic field, that is the fluctuation of the noise also reduced, that is a coherence time increase. So mostly it was limited by the magnetic field fluctuation. And the third one, which is like we improve the coherence by introducing extra pi pulse in the wait time region. So that has a name actually. So that is called spin echo pulse. Okay. So spin echo, what it does, spin echo actually we are applying this pi pulse in between 2 pi half pulse. So if in this pre-processing, if iron is accumulating some noise, it will be reversed. So by that way, it is uh, reducing the effect of noise and improving the precision. So that is why the coherence time also increased. Now, here we are changing the this wait time, and we are measuring the coherence time. The other thing what I was discussing, the effect of diffusion. So how do we know that the probe measure frequency is matching exactly with the energy gap of the slider, right? So because if it is diffused, then that will also introduce also some noise, right? Because will be unable to for the whole population, or you will be unable to measure the frequency. So that extension also you can do over here, like the last pulse, if you change the frequency, then you will see this kind of Ramsey fields, the right side, the field over here you can see. And these will tell you whether your probe meter is detained and how much it is detained. Okay. So here the black line, which is little carrier, that is from the Rabi spectroscopy. And the three is red color one, this is from the this Ramsey spectroscopy. So Ramsey spectroscopy will give you an idea, I mean very precisely, how far or how much is detained. Okay. So yeah, so this is the Ramsey field, what I was discussing. Here I'm discussing in yeah, so here what we are doing, you can see, you can visualize it like the blocks here also. Like we are applying pi by 2 pulse. Now, how are you going to apply pi by 2 pulse? You know from the Rabi oscillation. Now, if we apply pi by 2 pulse, basically it is a Hadamard gate. So you are bringing to the equator, right? And then in the waiting time, so this you are keeping it fixed for this kind of experiment, and you are changing the frequency of this, okay, with respect to this one, and then you are seeing this fringe, which is known as Ramsey fringe pattern. You will see this center fringe. They like out of these many fringes, few of them will be close to transferring all the population. If you fit in the now, you can write down the Hamiltonian for this one and then get you can get this population and this expression for the population in excited state for this kind of waiting time tau, and then you will get to know how much it is off from the uh, resonance. So now this is also another. Okay, this is yeah. Here, like you can see what I was explaining. Here, there is no spin echo pulse, but the right one you can see in between 2 pi by 2 pulse, I have applied 5 pulse. Okay, and here I was changing the phase of the last pi by 2 pulse, and you can see this oscillation, but the contrast is going down. If I increase the waiting time between 2 pi by 2 pulse. Okay. Now, when I have spin echo, then that contrast is improved. You can see compare with the left one, top left one and top right one figure. So the difference between two is one is only Raman spectroscopy, another one is one spin echo pulse is in between 2 pi by 2 pulse, and that is improving the coherence time. Okay, so this is the experimental realization. From theory also you will see it, and it is fitted with the dash line is fitted with here. So that is how I mean we can increase the precision for this one. Okay, here the animation is you see like how it is evolving in the blocks here, and yeah, and by having that extra pi pulse, how it is completely changing the phase from minus pi to plus pi. By that way, it is removing all the noises. Now there is one more thing. Now, in introduction section, we are talking about any unknown frequency which is reducing the which is reducing the precision. How do you get to know like what frequency it is? Because sometimes what happens when you are at the level of 10 to the power minus 18, because current atomic clock or ion clock is precision is around 10 to 15 to minus 18. And so in that level, or when you are detecting gravitational wave, you know how small it is in microvolts. So that time noise, how are you going to reduce the noise at that level? It is very difficult. The problem is that we don't know the frequency of that noise. If we know the frequency, then we have electronics you can fix it. The problem is to know the frequency. Okay, that is one more thing. Now, here, how are you going to know the frequency? Usual way of knowing the frequency. You have, so these left top figures, we already know this is the Rampus spectroscopy. And what we are doing here in the left one, if you see, here is in between 2 pi by 2 pulse in the wait time when there is no drive, no probe pulse, we are applying those unknown pulse, okay, the frequency of which one we want to determine. And now what is happening here, we are seeing the oscillation, okay, and because of this unknown pulse, we are observing this oscillation. Otherwise, what it's supposed to do? We are applying pi by 2 pulse, it brings ion from 0 state to the equator, and another pi by 2 pulse, it will bring from equator to the 1 state, right? But what is happening? It is oscillating. That is what we are observing because in the wait time or in between pi by 2 pulse, we have another pulse, which is the frequency of which we want to determine, and that is non-resonant. Okay, so and you see, like we are seeing this kind of oscillation, and if we see the oscillation, we can fit it, and we will know the frequency of it. Now, once we know the frequency, we can compensate because that is the important thing. How are you going to compensate? Now, if this is, let's say, your resonance frequency and this unknown frequency is on the blue side, then you have to give the apply the red side. So that is where it is denoted as compensating pulse here in the left bottom figure, if you see. So since you have already identified the frequency, so you can apply the compensating pulse, and then you can reduce it completely, the effect of that pulse completely. So this method is a soft. What you are doing, so you are applying another electric field, right? And because of this applied electric field, the energy level will be shifted up, right? That is why you are seeing the oscillations. Okay. So now, what are you trying over here? So you are seeing the oscillation by doing this Ramsey pattern measurement, and you know the frequency, then you are applying the compensating pulse. What does compensating pulse do? It is the same amount, but it is with the minus sign, so that it will reduce the effect of that unknown frequency or unknown signal. Okay, so this is we already know what I was explaining, the difference between Ramsey and Rabai. Now let's move to the so till now I have not talked about independent Hamiltonian. Whatever I was talking about, independent Hamiltonian, and the precision is given by Heisenberg. Now I'm going to talk about that precision can be, we can go beyond that precision if we apply time dependent Hamiltonian. And now if you want to estimate a parameter, so there is a bound which is Kramer-Rao bound. Now alpha is the parameter over here. If we want to measure alpha, then it is bounded by these factors. One is N, another one is F. F is the Fisher information, which is the amount of information about the parameter alpha that is contained in the data itself. And N is how many times you are doing the experiments or the large number of independent measurements. Now, the Fisher information is basically what? Fisher information is basically, so like the quantum states, what you are measuring, if they are very close enough, it is not possible to distinguish. So Fisher information is going to give you the measurement or is going to help you distinguish the eigenstates. Okay, that is the method. Now, here we are going to apply so for static Hamiltonian, you will see, and this is the form of Fisher information, how to calculate Fisher information. Psi alpha is the quantum states. And for static Hamiltonian, whether then the Fisher information will be proportional to P square. P square is again is the experimental time or observation time. And the uncertainty, as usual, it is will be delta alpha will be 1 by root over n and into t, because f alpha is proportional to t square. So this from the Kramer-Rao bound, it will be 1 by root over n and t. Now, what we are going to do it over here, or we are going to introduce time dependence in the Hamiltonian. So one more thing here we are going to do, we are going to start with, or we are going to prepare our system in the superposition state, and the Fisher information also, like if you write down, see the theory, then you can identify that you can write down in terms of eigenvalue, difference of eigenvalues. Okay. So this is the usual way, like the Ramsey spectroscopy, what we are doing. That is a similar way here also we are going to do. Is prepare the step preparation, and then we are this is the evaluation unitary operator, and then the measurement and the data preparation, because we have to evaluate the Fisher information. Yes, here it comes. So the here important thing what I was talking about, the time independent part is the H0. Okay, and this Hamiltonian we have already seen before. This is from the iron Hamiltonian, and this is the interaction part. And what we are doing it over here. So this energy level we are oscillating, we are modulating, okay, by an external field. So this thing I have already discussed over here in this while I was discussing this star shift measurement. Like we have a non-resonant pulse over here. Similar kind of measurement I'm going to explain over here. I'm going to explain here. Okay. So what I'm doing over here. So this energy level of this one is modulated. Okay. So that is how this omega is also varied. Now, on top of that, I am applying this Hamiltonian, which is basically a pi pulse. And important thing is that this pi pulse I am applying at the antinode of this oscillation or of this modulation. This is a sinusoidal modulation. You can see it over here. And this sinusoidal modulation, and on the antinode, we are applying a pi pulse. Why? We will come to that later slide. But just to understand, this is the Hamiltonian, this is the iron Hamiltonian, and one of the energy level is being modulated by applying an external electric field, sinusoidal electric field. And now, on top of that, we are applying this Hamiltonian or this probe. What it is doing? It is we are applying a pi pulse or the field at the antinode of this modulating. Okay. So since it is an external potential, it will introduce some like constant sharp shift, and there will be some modulated shift, right? Because it is modulating. The constant sharp shift will be there, and also modulating sharp shift will be there. Now, because we are giving this modulated pulse, so we first need to measure the sharp shift, how much sharp shift we are producing by applying this kind of pulse. So that has been measured over here, and it depends on whether you are on the blue side or on the red side. It depends on that. So, like what you are doing, that will tell us. Because okay, blue side and red side, it is with respect to the resonance. If it is more than resonance frequency, then it is blue side usually called, and if it is lower, it is on the red side. So here, this is the theoretical simulation. Like if you have only this Hamiltonian where there is no this control Hamiltonian, the control Hamiltonian, I'm talking about this one, this optimal control Hamiltonian, which we are applying on top of this Hamiltonian. So that is control Hamiltonian. If you do not have that Hamiltonian, then if we measure the QFI, it scales as T square. But when we have that Hamiltonian, extra optimal control Hamiltonian, this QFI is scaled as 2 to the power 4. This is from theory, and this is done by this guy. So they have phonetic theory. Now here comes the experimental part. So if you see it closely, you can see this whole system is kind of Ramsey spectroscopy experiment. But the important thing is that in the wait time sequence, there are 3 pulses. One is field evolution is there, and that unknown modulating pulse is there. And on top of that, this extra Hamiltonian, like which is used for optimal control, HLC, is there. So this is this modulation part, sin omega t, oscillating electric field, which is changing the upper energy level. Because here we want to know the unknown frequency, right? So that is why we need to modulate it. And we are scanning, and when it is matching, then we get to know. But on top of that, we are applying this optimal handle. So that is why we are applying qubit here ratio. So this is the picture of the external field what we are applying and where we are applying that extra pi field. And if you see the block sphere representation over here, like initially we prepare in the zero state, right? Initial state is denoted by this brown and then the final state with the green. So before pi by 2 applying pi by 2 pulse, it was in the zero state. Then it moves to the after pi by 2, it moves to the y state, right? Then it is freely evolving. Okay, so it is freely evolving because the evolution will be always there because of the energy difference between two layers. And after that, we are applying the control pulse. Okay, control pulse meaning the whole pulse, like this modulation already there, and on top of that is HLC. So this driving pulse is also there. After that, it is again it is really like the evolution is there, and then we are measuring by changing the phase. Because if the phase is not matching, then we are not able to see any population. So any information we are not going to get. Okay. But if you, so this is our whole Hamiltonian. It is not time independent Hamiltonian. It is time dependent Hamiltonian. Now, if we solve this, then this will be, so mu is here denoting the eigenvalue. Okay, so there will be two eigenvalues, and this is the evaluation of the eigenvalues. You can see both eigenvalues are crossing each other. It is crossing each other when this probe pulse is not there, then it is crossing. But when this probe pulse is there, this is trying to, this is trying to, so it will be clear over here. You can see from this figure, okay? Now, you see the pulse over here. When the pi pulse is there at the antinode, you see the effective after applying this pi pulse, it looks like this. As if it is trying to separate two close quantum states. If you can distinguish the quantum states very well, then you can increase the precision, right? Because quantum precision information is proportional to the for time. That is what we have seen from theory. It will be proportional to the 2 to the power 4, right? And quantum precision information is basically used for distinguish two close quantum states, and that is what is happening. That is the purpose of using pi pulse at the antinode. So, meaning this is the evolution of your all of your eigenvalues, and you are applying control pulse such that you are bringing the quantum states, two close quantum states far apart, so that you can easily identify, you can easily distinguish. Okay. So here, telling you once more time. So in the experimental process, this is your qubit, like, and one of the energy level we are what we are doing, we are modulating because we want to know the frequency. So that is the unknown frequency. The modulating signal, the frequency is unknown. And now on top of that, and so the frequency, how precisely we want to know, that depends on if we do not apply this pi pulse, this extra control pulse, then the precision will not increase. So by the way of applying this external pulse, we are trying to like bring apart those two quantum states. So by that way, we are easily, like, we are able to easily identify two close quantum states. That is the purpose of applying the pi pulse at the antinode. Now the question is why it is at the antinode? Why not any other position? That is also that I also will come in the later slide. But here I just want to point it out, depending on the problem. So here we are looking. So our problem is to know to determine the frequency. Okay, so that is why we are implementing at the antinode. But if you want to know the amplitude, then you have to implement at the node section. Now, how do we know? If the now the question is, how do we know that we are at the, because the pulse is unknown, right? You want to know So that is noise that is disturbing our clock precision. So this unknown one, how do we know we are at that? Because we don't know the frequency. If we know, then we can apply at the because there is one, right? That is the one. So then, so what we used to do. So this is the measurement that I can do. Yeah, yeah. You see the right side picture. So okay. So here, what we are doing, we are actually scanning the position of control pulse. Okay. When it is coming at the antinode, then QFI is maximum. So that is, you can see from this 3D plot, the QFI is maximum when F equals to F equals to 0. So you see, when it is at resonance, you can see, and when it is at the antinode. So by scanning, you will get to know that whether you are at the antinode or you are somewhere away from the antinode. So then the QFI value or quantitative information will be different. By that way, you can determine you are not. So that means what I'm trying to say, you can optimize your precision by introducing time-dependent Hamiltonian in such a way that you have full control. So that is the beauty of introducing time-dependent or starting time-dependent Hamiltonian. So this is the result, and we measure the sensitivity, how well we measure. So when it is controlled, it is following 1 over t square, and when it is uncontrolled, which is following the Heisenberg limit. And that is why we are saying like sensing beyond Heisenberg limit. Actually, sensing beyond Heisenberg limit, the difference is like the Hamiltonian is completely different. That is why we are saying the precision is quite high over here. Okay, I'm on time or hello? I'm still there. Or...
Yes, sir.
Okay, so I'm actually in the end. So I will just finish like what we are doing over here in the so the here this is again the Ramsey sequence you can see over here. So in the measurement side, what we are doing, we actually measure the population. That is what I told you before. So we are measuring the population, and that is having the information of phase. And every time we are getting this kind of slope, from the slope we are getting d phi df, and that is being plotted over here, and that gives us the sensitivity, which is 1 over t square for time dependent Hamiltonian. Now, if you see this plot over here in the left side, this is the sensitivity plot. This is time. This is what time? This is the time how long we are applying the unknown pulse. Okay. Now, you can see after like 80 or 90, the data start really deviating from this straight line. Straight line is showing the 1 by t square. Why it is deviating? Because our system coherence time actually 85 microseconds or something like that. So that is why if it is not beyond coherence, I mean below coherence time, it will start deviating. So that is also another reflection. If you do this, you will know what is the actual coherence time. But if you do only Ramsey, like you have only time independent Hamiltonian, you do only Ramsey spectroscopy, so it will not give us that precise value because that measurement tells gives us 500 microseconds, but this measurement tells us our coherence time is around 80 or 90 microseconds. So that is another thing. Now, one more thing: how do we get like how do we what we are doing, like how long we are applying, that is okay. How long we are applying this unknown pulse, that is okay. But how, what does it mean? Meaning this pulse, this is the unknown pulse we are applying. Now, how long meaning, how many pi pulse, like control pulse we are applying? That is the meaning of this. Let's say we are taking, so this is the 100 microsecond total pulse. Now 100 microsecond, how many pulse we are applying? So 1, 2, 3, 4, 5, 6, 7 pulse we are applying. Now if I'm taking 50 microsecond, then I'm applying only 1, 2, 3 pulse. So that is the meaning of this time. Yeah, time over here, and in each case we are measuring the sensitivity, frequency uncertainty, or the sensitivity of the frequency. Now, this is the method. This is the method. Yeah, it is very useful. Like the importance of this one, I have already discussed. The other thing is that if we can not only frequency, but we can also measure amplitude very precisely. So that also we have done it, but it is not very like the other one of this, but it will be 1.5, and that is reflected over here. But in this case, in order to improve the precision, we have to implement the control pulse at the node of the stem, the node of the unknown phase. So that is the difference. Okay. So now, so we know accurate timekeeping is necessary for many things. Now, why precision maps? So that is I already described, but these are the things what I want to point it out, because recently also India is, I mean, looking for like all these processes, it's targeting for developing some precision technologies or something like that. So if it is precise, then you know the poison very well. That is the penalty we can say. And the application wise, you can see the way. So I'm going to stop here. So I would love to if anybody has any questions. Hello?
Yes, sir.
Yeah, so I'm stopping here. So
Thank you very much, sir. Participants are encouraged to put their query in the chat box. You have taken the 2 hours lecture continuously without
yeah,
any.
yes, yeah. Actually, I had also class before. So this time I was talking about quantum sensing. Last time I was thinking in the same department, because last time I was talking about quantum algorithms. So quantum sensing, that time I didn't share. So yeah. And one more thing I just want to announce, because we are also taking students. We want to develop quantum computer here in University of Hyderabad. So any students who are willing to do any project, like at least, or also PhD students, postdocs, welcome to apply. So yeah.
So it's a good opportunity for our students also, because many of us are PhD scholars and faculties. So faculties can encourage their students to work with sir.
Yes, and also like for postdoc, we can apply for those government fund is already there, right? Many projects are there for postdocs also. We can write project and do those. So please communicate with me. So yeah.
So
And yeah, if you are unable to I mean ask questions, you can send me an email. Yeah, so I
yes,
happy
if
to
there
answer.
is any queries, and I will
Yes.
put your email. And the students are also having your email, so they can directly contact with you. And the
Yeah.
faculty members which are interesting with your work, because in the whole lecture I saw your papers are also working, having a very good work. So I think by taking your reference in the paper references, many of us can do a little bit good work. I think that will be a good reference for us. So I think there are no queries.
Okay.
Maybe after seeing your lecture on the YouTube,
Yes.
the participants may mail us that we want to something like that, what will be their confusion. Then I will be in touch with you. So
Okay.
thank you.
Yeah. So one more thing. One more thing I just want
Yes,
to
yes,
add.
please.
Like few of the figures you may, I mean, like regarding atomic clock, I have taken from Dave Wineland, who got Nobel Prize. So I took from his slide, and a few from, I mean, you just Google it, you will get it, and few from our government website also. Yeah. That's okay. Thank you.
Okay. Thank you, doctor, for taking 2 hours continuous time for us. So it will be very beneficial lecture for us for the quantum sensing course. So thank you once again from the participant side and MNIT Jaipur and APSCHE.
Thank you, sir. Thank you.